When I say that the universe is not real, it often triggers immediate confusion or even resistance. It sounds like something philosophical, abstract, or even irrational. Most people instinctively assume reality is straightforward. There is a physical world made of objects, space, time, and matter, and we simply exist inside it as observers. But modern physics, especially quantum mechanics and foundational theories of spacetime, forces us to rethink that assumption completely. To be clear, this is not a claim that nothing exists. It is not a suggestion that reality is an illusion in the simplistic sense, or that we are living in a fictional simulation. The idea is far more subtle and far more profound. What we call the universe, the three-dimensional world filled with solid objects, flowing time, and measurable distances, is not the deepest layer of reality. Instead, it is an emergent structure. It is a secondary description that arises from something more fundamental, or something that does not behave like the physical world we experience at all. To understand this, we must begin with a shift in perspective. Physics no longer describes reality as a collection of objects moving through space. Instead, it describes reality as a mathematical object, a quantum state evolving according to precise rules. At the most fundamental level, everything is described by what physicists call a wave function. This wave function does not represent physical objects in space. Instead, it represents probabilities, a complete mathematical description of all possible outcomes that could ever occur. In this framework, reality is not made of things in the traditional sense. There are no definite particles with fixed positions, no absolute trajectories, and no rigid structures at the deepest level. Instead, there is only a constantly evolving mathematical structure containing possibilities. This is where the key shift happens, what we perceive as physical reality, where stable objects, solid matter, and consistent space is not fundamental. It is what emerges when this underlying quantum structure is observed, interacted with, or measured. In other words, the universe we experience is not the base layer. It is the surface layer, a projection of deeper mathematical rules. To make this more intuitive, imagine a video game. Inside the game, you see characters, buildings, landscapes, and physics that feel real within that world. But underneath it all is code A, or a set of instructions running on a computer. The game world is not fake, but it is not fundamental either. It is an emergent experience created by underlying computation. Similarly, the physical universe we experience behaves like a rendered environment built from deeper informational rules. Quantum mechanics reinforces this idea in a very uncomfortable way for classical intuition. At the quantum level, particles do not behave like solid objects with definite properties. Instead, they exist in superpositions, combinations of multiple possibilities existing at once. An electron, for example, does not have a single definite position until it is measured. Before measurement, it is described by a wave function spread across many possible locations. It is not simply unknown, it genuinely does not have a fixed position in the classical sense. This forces us to confront a deep question. If something does not have definite properties, in what sense is it real? Classical physics assumes that objects have properties, whether we observe them or not. Quantum physics challenges this assumption. It suggests that properties become definite only through interaction, through observation, measurement, or entanglement with an environment. This leads directly into the measurement problem, one of the most fundamental unresolved questions in physics. When exactly does a quantum system stop being a set of possibilities and become a single outcome? Some interpretations suggest that observation itself plays a crucial role. Others argue that decoherence, the interaction of quantum systems with their environment, causes the appearance of classical reality by spreading quantum information into the surroundings until interference becomes impossible. Either way, the result is the same. The world we perceive as solid and definite is not fundamental. It is an emergent approximation created when quantum possibilities stop interfering with each other. This means that the real, the world we experience, is not a direct reflection of fundamental reality. It is a filtered, simplified version of a much deeper quantum structure. To understand how radical this is, consider this. Every object you see, your surroundings, your body, even your thoughts, is ultimately built from quantum states that do not behave like classical objects. The solidity you experience is not a property of the fundamental layer. It is a consequence of how information is processed at higher levels of complexity. In this sense, reality is not a collection of things. It is a process, a continuous unfolding of quantum information that only appears classical when observed from a limited perspective. This leads to a profound conclusion. The universe is not real in the way we intuitively assume. It is not a fixed classical structure existing independently in space and time. Instead, it is a dynamic informational system that only appears classical at the level of human experience, what we call. Reality is therefore not the foundation of existence. It is the interface through which we interact with a deeper, more abstract layer of mathematical structure. And once this idea is understood, everything else, space, time, matter, and even existence itself begins to look very different. To understand why modern physics challenges the idea of a real, solid universe, we have to go directly into the heart of quantum mechanics, the most successful yet most counterintuitive theory ever developed. At the level of everyday experience, reality feels stable and predictable. Objects exist in specific places. Events follow a clear timeline, because leads to effect in a logical sequence. A ball is either here or there. A light switch is either on or off. This is the classical picture of reality that human intuition evolved to understand. But quantum mechanics reveals that this picture is not fundamental. It is only an approximation that works at large scales. When we zoom into the smallest levels of existence, atoms, electrons, photons, reality stops behaving like a collection of solid objects and starts behaving like something far more abstract, a system of probabilities. In quantum physics, particles do not have definite properties before they are measured. Instead, they exist in what is called a superposition, a combination of all possible states at once. An electron is not simply at one location or another. It exists as a spread out wave of probability described mathematically by a wave function. This wave function is not a physical wave in space. It is an abstract mathematical object that encodes every possible outcome the electron could have if measured. Until a measurement occurs, the electron does not have a single definite position in the classical sense. This is already a radical departure from everyday intuition. But the deeper implication is even more disturbing. Reality at the quantum level is not fixed. It is not that we simply lack knowledge of where the particle is. Rather, the particle does not have a definite position until it interacts with something that forces a specific outcome to emerge. This leads directly to one of the most famous thought experiments in physics, Schrödinger's cat. In this scenario, a cat is placed in a sealed box with a quantum device that has a 50% chance of triggering a deadly event. According to quantum mechanics, until the box is opened, the system exists in a superposition, meaning the cat is simultaneously alive and dead. This is not meant to be taken literally as a biological claim. It is meant to highlight the absurdity of applying quantum rules to macroscopic objects, but it exposes a deeper truth. If quantum mechanics is universally valid, then there is no clear boundary between the quantum and classical world. The question then becomes, when does reality become definite? This is known as the measurement problem. It is one of the deepest unresolved issues in physics. The mathematics of quantum mechanics works perfectly. It predicts experiments with extreme precision. But the interpretation of what is actually happening remains unclear. One interpretation, often called the Copenhagen interpretation, suggests that the act of measurement causes the wave function to collapse. Before measurement, there are only probabilities. After measurement, there is a single outcome. But this raises a serious problem. What exactly counts as a measurement? Does it require a conscious observer, a measuring device, an interaction with the environment? Where is the precise boundary between quantum possibility and classical reality? This ambiguity suggests something very important. Classical reality may not be fundamental at all. It may simply be what emerges when quantum systems become large, complex, and entangled with their environment. This process is known as decoherence. Decoherence explains how quantum systems lose their ability to interfere with each other when they interact with the surrounding environment. As a system becomes entangled with countless particles around it, its quantum behavior becomes effectively hidden. The different possible outcomes no longer interact in observable ways. From the perspective of an observer inside one branch of this process, it looks like a single definite outcome has occurred. It appears as if the wave function has collapsed into one reality. But in the deeper mathematical description, all possibilities still exist. They simply no longer interfere with each other. This leads to a striking conclusion. The classical world we experience is not the full picture. It is one branch of a much larger quantum structure. Reality in this sense is not a single fixed story. It is a branching network of possibilities, all coexisting within the underlying wave function. Each observer experiences only one branch. That branch feels completely real, solid, consistent, and definite. but from a deeper perspective it is. We're only one slice of a much larger structure containing many parallel outcomes. This is where the concept of reality begins to dissolve into something more abstract. The universe is not a single, well-defined object. It is a constantly evolving mathematical structure, where definiteness emerges only locally through interaction and observation. Even more importantly, this means that what we call physical reality is not independent of observation. It is not a fixed backdrop that exists regardless of whether anyone looks at it. Instead, it is a result of interaction between quantum systems. This does not mean reality is arbitrary or imaginary. The underlying quantum rules are extremely precise and objective. But the classical world, the world of definite objects and outcomes, is not fundamental. It is derived. In this view, the universe is not a static collection of things. It is an unfolding process of quantum information, where reality appears stable only because of how information spreads and becomes inaccessible between different branches. The implication is profound. What we experience as the real world is actually an emergent snapshot of a deeper quantum reality that is far more complex, fluid, and interconnected than anything classical intuition can capture. And once we accept this, the next question naturally arises. If space itself is not fundamental, then what is it really? Once quantum mechanics challenges the idea of a solid, definite reality, the next shock comes from an entirely different area of physics: gravity, black holes, and the structure of space-time itself. For centuries, we assumed space was the stage of the universe, a three-dimensional container in which everything exists. Objects have positions in space. Distances separate things. Space feels like the most basic backdrop of reality. But modern theoretical physics suggests something far more radical. Space itself may not be fundamental. One of the most surprising ideas to emerge from black hole physics is the holographic principle. This principle suggests that everything happening inside a volume of space can actually be described by information stored on its boundary. In other words, a three-dimensional region of space may be fully encoded on a two-dimensional surface. This is not science fiction. It comes directly from attempts to understand black holes. When physicists studied black hole entropy, they discovered something unexpected: the amount of information inside A. A black hole does not scale with its volume. Instead, it scales with the area of its event horizon. This means the information content of a black hole is proportional to its surface, not its interior. That discovery led to a shocking conclusion. The interior of a black hole may not contain independent physical reality in the way we imagine. Instead, everything that falls in could be encoded on the boundary. If this idea is taken seriously and generalized, it leads to a profound possibility. The entire universe might work like a hologram. A hologram is a two-dimensional surface that encodes a three-dimensional image. The image appears fully real and spatial, but the underlying information is actually stored in two dimensions. Similarly. The holographic principle suggests that our three-dimensional universe may be a projection of information encoded on a distant two-dimensional boundary of space-time. This does not mean we are living in a fake world. It means that what we perceive as depth, volume, and spatial structure may not exist at the most fundamental level. Instead, space could be an emergent phenomenon, something that arises when underlying information is interpreted in a particular way. This idea becomes even more concrete in theoretical physics through something called the ADS/CFT correspondence discovered by Juan Maldesna. This framework shows that a gravitational theory in a three-dimensional space can be mathematically equivalent to a quantum theory on its two-dimensional boundary. In this duality, the interior space with gravity, geometry, and even black holes is not fundamental. It is fully described by a lower dimensional system without gravity. This is one of the strongest pieces of evidence that space-time itself may not be fundamental. If one description contains gravity and space and the other does not, yet both describe the same physics perfectly, then space cannot be the deepest layer of reality. It must be derived. This leads to radical reinterpretation of existence. The world we experience as three-dimensional may actually be a projection of deeper informational rules encoded elsewhere. In this view, we are not truly moving through space in the way we intuitively believe. Instead, what we experience as spatial relationships may emerge from patterns of information and entanglement. Space, then, is not a container. It is a consequence. But this idea becomes even more striking when we consider that space is not the only illusion. Time itself also begins to break down at the fundamental level. In many approaches to quantum gravity, time does not exist in the way we experience it. The equations describing the universe at the deepest level do not include a flowing time. Instead, they describe relationships between quantum states that do not evolve in a traditional sense. Time appears only when we observe correlations between parts of a system. It is not a background parameter. It is something constructed from a change in interaction. This suggests that both space and time, the entire fabric of space-time, are not fundamental. They are emergent. They arise from something deeper. Quantum information and entanglement. Entanglement in particular plays a key role. Modern research suggests that the structure of space may actually be built from entanglement connections between quantum systems. Where there is more entanglement, space appears closer. Where there is less, space appears distant. This means that geometry itself may be a secondary effect of information relationships. In this framework, the universe is not a vast, empty space filled with objects. It is a dense network of quantum relationships, and space is what this network looks like when viewed at large scales. From this perspective, the universe is not a stage where things happen. It is a dynamic informational structure where space is just one way of interpreting deeper connections. Even black holes reinforce this idea. The inside of a black hole, once thought to be a region of extreme space-time curvature, may not be an independent physical region at all. Instead, all information about it may be stored on its boundary, suggesting that what we think of as inside space is actually encoded externally. If this is true, then the most basic assumption of human experience, that we live inside a three-dimensional space, is not fundamental. It is emergent. And once space itself becomes questionable, we are forced to confront an even deeper question. If neither space nor time is fundamental, then what is reality actually made of? If quantum mechanics removes the certainty of objects and the holographic principle removes the certainty of space, then the next layer of breakdown concerns something even more fundamental. The idea of a single, objective reality shared by everyone. In everyday life, we assume reality is independent of us. We believe the world exists in a definite way whether anyone is looking at it or not. Two people can observe the same event and in principle agree on what happened. This assumption forms the foundation of classical thinking. But quantum physics challenges this deeply. At the quantum level, reality does not behave like a fixed structure waiting to be observed. Instead, it behaves more like a system that only becomes definite through interaction. This leads to one of the most controversial ideas in modern physics. Reality may be observer-dependent at a fundamental level. To understand this, we must revisit what observation actually means in quantum mechanics. In classical physics, observation is passive. You look at something that already exists in a definite state. But in quantum mechanics, observation is active. The act of measuring a system changes what can be said about it. Before measurement, a system exists in a superposition of multiple possibilities. After measurement, only one outcome is experienced. But the question is, what determines this outcome and why? This leads to a deeper interpretation known as the participatory universe, strongly associated with physicist John Wheeler. In this view, observers are not separate from reality. They are part of the process that brings reality into definite form. In other words, reality is not something that exists fully formed. It is something that becomes definite through interaction between systems. This shifts the role of the observer dramatically. The observer is not a passive witness of awe or pre-existing world. The observer is part of the mechanism through which the world becomes defined. This idea becomes even more interesting when we consider that different observers can experience different realities depending on their information. In relativity, we already accept that observers in different motion states experience different measurements of time and space. But quantum mechanics goes further. It suggests that even the outcome of events may not be globally fixed in the way where classical physics assumes. Instead, what is real for one observer may not be identical to what is real for another until they interact and compare information. This does not mean reality is chaotic or arbitrary. The underlying quantum state is still governed by precise mathematical laws. But the classical story that emerges from it depends on perspective. This leads to a crucial distinction. The quantum state is objective and universal. The classical reality we experience is contextual and relational. This is a subtle but powerful shift. It means there is no single view from nowhere that describes reality exactly as it is in all contexts. Instead, reality is always described from within the system by observers embedded inside it. This is why some interpretations of quantum mechanics suggest that reality is fundamentally relational. Objects do not have absolute properties. They have properties only in relation to other systems. For example, a particle does not have a definite or position in absolute space. It has a position relative to a measurement interaction. Without that interaction, the property is not defined. This leads to a very different picture of the universe. Instead of a single fixed structure, we get a network of relationships. Reality becomes something that exists only through interactions between parts of the system. This raises a profound philosophical question. If reality depends on observation, does that mean consciousness creates reality? The answer in modern physics is more careful and less mystical than it might first appear. Quantum mechanics does not require human consciousness specifically. Any physical interaction that produces irreversible information transfer can act as a measurement. This includes detectors, environments, and other quantum systems. In most modern interpretations, consciousness is not required to collapse reality. However, what is required is interaction. Without interaction, there is no definite outcome. This means reality is not independent of relationships between systems. It emerges through connection. This is a key insight. Reality is not a standalone object, it is a web of interactions. Even the idea of a single global reality becomes questionable. Different observers, each with their own limited access to information, construct their own consistent versions of events. These versions agree when information is shared, but before that, they are not necessarily identical in a global sense. This is not subjective reality in the psychological sense. It is a structural feature of quantum theory itself. It means reality is not something fully written in advance. It is something that unfolds through interaction. This becomes especially clear in extreme physics scenarios like black holes. An observer falling into a black hole and an observer outside it describe completely different experiences of the same system. From one perspective, the object crosses the horizon smoothly. From another, it never does. Both descriptions are internally consistent, yet they cannot be combined into a single classical narrative. This suggests that there is no single God's eye view of the universe that contains all facts in a classical sense. Instead, reality is always tied to a frame of observation. This leads to a deeper conclusion. What we call the universe is not a single fixed object. It is a collection of interrelated perspectives, all arising from the same underlying quantum structure, each. A perspective is real within its domain, but no single perspective captures the whole in classical terms. And once we accept this, we begin to see that reality is not something we simply observe, it is something we participate in. This brings us to the final and deepest layer of the discussion. If reality is relational, emergent, and mathematical, then what does that mean for meaning, consciousness, and existence itself? If we follow the ideas of quantum mechanics, holography, and observer-dependent reality to their deepest level, we arrive at a conclusion that completely reshapes how we think about existence itself. The universe, as we usually imagine it, a physical container filled with objects moving through space and time, dissolves into something far more abstract. At its foundation, reality appears less like a thing and more like a structure. And that structure is increasingly described not in physical terms, but in mathematical ones. Modern physics already points strongly in this direction. The laws governing particles, forces, space-time, and quantum fields are all written in mathematical language. But the deeper suggestion, one that many theoretical physicists seriously consider, is even more radical. Mathematics is not just a tool to describe the universe. It may be what the universe actually is. In this view, physical reality is not made of matter in the traditional sense. Instead, it is made of mathematical relationships, patterns, or structures that give rise to what we interpret as matter, space, and time. This is the core idea behind the mathematical universe hypothesis, which proposes that the physical world is not merely described by mathematics, it is mathematics. If this is true, then everything we experience as physical reality, objects, energy, space, time is an emergent interpretation of a deeper mathematical structure. We are not living inside a physical container. We are patterns within an abstract system of relationships. This leads to a striking redefinition of existence. What we call real is not something made of physical substance, but something that exists as a consistent mathematical structure with internal rules and relationships. From this perspective, particles are not tiny physical objects. They are excitations or representations of deeper mathematical symmetries. Fields are not substances filling space. They are mathematical entities defined across abstract spaces. Even space-time itself becomes a derived concept emerging from deeper informational or algebraic structures. The more deeply physics progresses, the further it moves away from intuition and closer to abstraction. And this raises an important question. If reality is mathematical at its core, why do we experience it as physical? The answer likely lies in how conscious observers arise within this structure. We are not separate from the universe we observe. We are part of it, embedded within it as self-organizing patterns of information. Our brains, our perceptions, and our thoughts are all processes occurring within the same underlying mathematical framework. What we call conscious experience may be the internal perspective of certain complex informational structures interpreting themselves from the inside. This leads to a powerful idea. Consciousness and physical reality may not be separate categories. Instead, they may be two different descriptions of the same underlying process. One describes it from the outside, physics, and the other from the inside, experience. From this point of view, consciousness does not need to emerge from matter as something extra. Instead, both matter and consciousness may be different expressions of the same deeper informational reality. This does not solve the hard problem of consciousness, but it reframes it. Instead of asking how physical matter creates subjective experience, we can ask how a single underlying structure gives rise to both internal and external descriptions. In this framework, the separation between mind and matter becomes less absolute. It becomes a matter of perspective rather than substance. This also changes how we interpret meaning in life. If the universe is fundamentally mathematical, does that make existence cold or meaningless? Surprisingly, the opposite may be true. Meaning does not require physical substance. Meaning arises from structure, relationships, and experience. Even if love, emotion, and thought emerge. From deeper informational processes, they are still real at the level where they exist. Emergence does not mean illusion. It means layered reality where higher levels have their own valid truths, even if they arise from deeper foundations. For example, a sunset is explained by physics, light scattering through atmospheric particles. But this explanation does not cancel the beauty of the experience. The beauty is real at the level of perception, even though it emerges from physical processes. Or similarly, human experience, love, grief, curiosity, creativity remains real and meaningful, even if it arises from deeper mathematical or quantum structures. In fact, recognizing the deeper structure of reality can increase a sense of wonder rather than reduce it. The universe becomes not less meaningful, but more intricate and extraordinary than we imagined. We are not random collections of matter floating in space. We are self-aware structures within a vast informational system capable of reflecting on itself. In a sense, the universe becomes aware of itself through us. We are not separate from reality. We are expressions of it that can observe and interpret it. This transforms the question, what is the universe, into something deeper. The universe is not just something we live inside, it is something that, through us, begins to understand itself. And this leads to the final insight. When we say the universe is not real, we do not mean it is meaningless, imaginary, or unimportant. We mean it is not what it appears to be at the surface level. It is not a collection of solid objects in a fixed space. It is not a static stage where events unfold independently of observation. Instead, it is a dynamic, relational, mathematical, and informational structure. It is quantum at its core, emergent at its surface, and conscious in its self-observing aspects. Reality is layered. What we experience is real, but it is not fundamental. What is fundamental is